Hey, hi guys. So today is pretty interesting because we'll go through Attention is All You Need paper, which has actually transformed the whole GenAI journey. Um, it is This is actually the um, start of the whole thought process, um, where actually, if you look at it, it is actually a one-step improvement on top of the journey, that is RNN, LSTM, and LSTM's I would say performance optimizer. Um, um, so uh, GRU, um, but uh, still we have challenges with respect to the way we process with LSTM, the way we how much data that we can run using LSTM and stuff. There are challenges with it. So um, Attention is All You Need is a paper which came as a storm, which addressed all those issues. And also, it gave us a confidence saying we can train models with huge amounts of data, uh, which is nothing but the large language models. Um, and um, they bring in parallelism into it to improve performance and stuff, right? So um, instead of me briefing on it, we'll study it, and then at the end, maybe we'll have a discussion either today or tomorrow. It's gonna take some time, but this is need of the hour. Let's get to it. Choose a tab. Okay, let's go.
Welcome to my video about the transformer, and this is actually the version 2.0 of my series on the transformer. I had a previous video in which I talked about the transformer, but the audio quality was not good, and as suggested by my viewers, as the video was really had a huge success, the viewers suggested me to improve the audio quality. So this is why I'm doing this video. You don't have to watch the previous series because I will be doing basically the same things, but with some improvements. So I'm actually compensating from some mistakes I made or from some improvements that I could add. After watching this video, I suggest watching my other video about how to code a transformer model from scratch. So how to code the model itself, how to train it on a data, and how to inference it. Stick it with me because it's gonna be a little long journey, but for sure worth. Now, before we talk about the transformer, I want to first talk about recurrent neural networks. So the networks that were used before they introduced the transformer for most of the sequence to sequence jobs, tasks. So let's review them. Recurrent neural networks existed a long time before the transformer, and they allowed to map one sequence of input to another sequence of output. In this case, our input is X, and we want an input sequence Y. What we did before is that we split the sequence into single items. So we gave the recurrent neural network the first item as input, so X1, along with an initial state, usually made up of only zeros, and the recurrent neural network produced an output, let's call it Y1. And this happened at the first time step. Then we took the hidden state, this is called the hidden state of the network of the previous time step, along with the next input token, so X2, and the network had to produce the second output token, Y2. And then we did it the same procedure at the third time step, in which we took the hidden state of the previous time step along with the input state, the input token at the time step 3, and the network had to produce the next output token, which is Y3. If you have n tokens, you need n time steps to map a n sequence input into an n sequence output. This worked fine for a lot of tasks, but had some problems. Let's review them. The problems with recurrent neural networks, first of all, are that they are slow for long sequences because think of the process we did before. We have kind of like a for loop in which we do the same operation for every token in the input. So if you have the longer the sequence, the longer this computation. And this made the network not easy to train for long sequences. The second problem was the vanishing or the exploding gradients. Now, you may have heard these terms or expression on the internet or from other videos, but I will try to give you a brief insight on what do they mean on a practical level. So as you know, frameworks like PyTorch, they convert our networks into a computation graph. So basically, suppose we have a computation graph. This is not a neural network. Okay? I will be making a computational graph that is very simple, has nothing to do with neural networks, but will show you the problems that we have. So imagine we have two inputs, x, and another input, let's call it y. Our computational graph first, let's say, multiplies these two numbers. So we have first a function, let's call it f of x and y. That is x multiplied by y, multiplied. And the result, let's call it z, is given to another function. Let's call this function g of z is equal to, let's say, z squared. What our PyTorch, for example, does is that PyTorch want to calculate usually we have a loss function. PyTorch calculates the derivative of the loss function with respect to each weight. In this case, we just calculate the derivative of the g function, so the output function with respect to all of its inputs. So the derivative of g with respect to x, let's say, is equal to the derivative of g with respect to f and multiplied by the derivative of f with respect to x. These two should kind of cancel out. This is called the chain rule. Now, as you can see, the longer the chain of computation, so if we have many nodes one after another, the longer this multiplication chain. So here we have 2 because the distance from this node and this is 2, but imagine you have 100 or 1000. Now imagine this number is 0.5 and this number is 0.5 also. The resulting numbers, when multiplied together, is a number that is smaller than the two initial numbers. It's going to 0.25 because it's 1 half multiplied by 1 half is 1/4. So if we have two numbers that are smaller than 1 and we multiply them together, they will produce an even smaller number. And if we have two numbers that are bigger than 1 and we multiply them together, they will produce a number that is bigger than both of them. So if we have a very long chain of computation, it eventually will either become a very big number or a very small number. And this is not desirable, first of all, because our CPU or our GPU can only represent numbers up to a certain precision, let's say 32-bit or 64-bit. And if the number becomes too small, the contribution of this number to the output will become very small. So when the PyTorch or our automatic, let's say, our framework will calculate how to adjust the weights, the weight will move very, very, very slowly because the contribution of this product will be a very small number. And this means that we have the gradient is vanishing, or in the other case, it can explode, become very big numbers. And this is the problem. The next problem is difficulty in accessing information from a long time ago. What does it mean? It means that, as you remember from the previous slide, we saw that the first input token is given to the recurrent neural network along with the first state. Now, we need to think that the recurrent neural network is a long graph of computation. It will produce a new hidden state. Then we will use the new hidden state along with the next token to produce the next output. If we have a very long sequence of input sequence, the last token will have a hidden state whose contribution from the first token has nearly gone because of this long chain of multiplication. So actually, the last token will not depend much on the first token. And this is also not good because, for example, we know as humans that in a text, in a quite long text, the context that we saw, let's say 200 words before, still relevant to the context of the current words. And this is something that the RNN could not map. And this is why we have the transformer. So the transformer solves these problems with the recurrent neural networks, and we will see how. The structure of the transformer, we can divide into two macro blocks. The first macro block is called the encoder, and it's this part here. The second macro block is called the decoder, and it's the second part here. శ్రీగ్రామం అగ్నిహోత్రి శాస్త్రికి లీలా మహత్యము చూపించి శ్యామను బతికించి విప్పాము విషం తొలగించి భక్త విషయరూపం భక్త భీమాజికి క్షయరోగం నశించనతని సహనం ఊది వైద్యము చేశావు వ్యాధిని న్యాయము చేశావు కాకాజీకి ఓ సాయి విఠలు దర్శనం సంతానం
You in RNN, what you do is you produce the output and you pass the combination of input and output together. Whereas LSTM, you use the combination for of both, but at the same time, you run a parallel that in Sunday of X in parallel. So that is how you retain the context for longer term. So, computational complexity. Augmented.
the same number as this cat here because they occupy the same position in the vocabulary. We take these numbers, which are called input IDs, and we map them into a vector of size 512. This vector is a vector made of 512 numbers, and we always map the same word to always the same embedding. However, this number is not fixed. It's a parameter for our model. So our model will learn to change these numbers in such a way that it represents the meaning of the word. So the input IDs never change because our vocabulary is fixed, but the embedding will change along with the training process of the model. So the embedding numbers will change according to the needs of the loss function. So the input embedding are basically mapping our single word into an embedding of size 512. And we call this quantity 512 the model because it's the same name that it's also used in the paper. Attention is all you need.
Let me show you how we do stuff around here.
Actually, my department uses Monday.com, so I'm good.
The work management tool.
Let's look at the next layer of the encoder, which is the positional encoding. So what is positional encoding? What we want is that each word should carry some information about its position in the sentence. Because now we built a matrix of words that are embeddings, but they don't convey any information about where that particular word is inside the sentence. And this is the job of the positional encoding. So what we do, we want the model to treat words that appear close to each other as close and words that are distant as distant. So we want the model to see this information about the spatial information that we see with our eyes. So for example, when we see this sentence as positional encoding, we know that the word what is more far from the word is compared to encoding because we have this spatial information given by our eyes, but the model cannot see this. So we need to give some information to the model about how the words are spatially distributed inside of the sentence. And we want the positional encoding to represent a pattern that the model can learn. And we will see how. Imagine we have our original sentence, your cat is a lovely cat. What we do is we first convert into embeddings using the previous layer, so the input embeddings, and these are embeddings of size 512. Then we create some special vectors called the positional encoding vectors that we add to these embeddings. So this vector we see here in red is a vector of size 512, which is not learned. It's computed once and not learned along with the training process. It's fixed. And this vector represents the position of the word inside of the sentence. And this should give us an output that is a vector of size, again, 512, because we are summing this number with this number. This number with this number. So the first dimension with the first dimension, the second dimension with that. So we will get a new vector of the same size of the input vectors. How are these position embedding calculated? Let's see. Imagine we have a smaller sentence. Let's say your cat is, and you may have seen the following expressions from the paper. What we do is we create a vector of size D model, so 512, and for each position in this vector, we calculate the value using these two expressions. Using these arguments. So the first argument indicates the position of the word inside of the sentence. So the word your occupies the position 0. And we use for the even dimension, so the 0, the 2, the 4, the 510, etc., we use the first expression, so the sign. And for the odd positions of this vector, we use the second expression. And we do this for all the words inside of the sentence. So this particular embedding is calculated PE of 10 because it's the first word embedding 0. So this 1 represents the argument pause, and this 0 represents the argument 2i. And PE of 1 means that the first word dimension 1. So we will use the cosine, giving the position 1, and the 2i will be equal to 2i plus 1 will be equal to 1. And we do this for the third word, etc. If we have another sentence, we will not have different positional encodings. We will have the same vectors, even for different sentences, because the positional encoding are computed once and reused for every sentence that our model will see during inference or training. So we only compute the positional encoding once. When we create the model, we save them, and then we reuse them. We don't need to compute it every time we feed a sentence to the model. So why the authors chose the cosine and the sine functions to represent positional encodings? Because let's watch the plot of these two functions. You can see the plot. PE of 1 means that the first word dimension 1. So we will use the cosine, giving the position 1, and the 2i will be equal to 2i plus 1 will be equal to 1. And we do this for the third word, etc. If we have another sentence, we will not have different positional encodings. We will have the same vectors, even for different sentences, because the positional encoding are computed once and reused for every sentence that our model will see during inference or training. So we only compute the positional encoding once. When we create the model, we save them, and then we reuse them. We don't need to compute it every time we feed a sentence to the model. So why the authors chose the cosine and the sine functions to represent positional encodings? Because let's watch the plot of these two functions. You can see the plot is by position, so the position of the word inside of the sentence, and this depth is the dimension along the vector, so the 2i that you saw before in the previous expressions. And if we plot them, we can see, as humans, a pattern here, and we hope that the model can also see this pattern. Okay, the next layer of the encoder is the multi-head attention. We will not go inside of the multi-head.
Position, depth. There's a pattern, I don't know. Sine 0 by 2i 1000 power 2i getting more. You calculate, you'll see, but it is a static number. It will be same as you're saying. The 100 volts original encoding will be the same. But let's say sine of um, the business going to the pattern that can be learned by the model. Okay. Okay, for now let's, so first thing that we will learn is first of all words sequence is taken. Vector are added to which are fixed values basing on position. So okay, now let's see. Not I understand this. Okay. Zero index of token 0, 1, 2, 3. This is quick run. Dimension of the output embedding space. Mhm. So if you take the 3, the first number is 3i, that is 6. So sine of 3 by 10,000 power 6 by 512. Hey, what is I, man? Pause is position, it is k. I is the use. Okay, okay. Okay. denominator is always the same. Okay. Denominator is power n comma 2i by d. D is the equation. Oh, no, D is fixed now. Oh, for sample purpose, he's given D is equal to 4. 4, then it is 0, 0, 0, 0, 2, 0, 4. 1, 0. Okay, let's start by looking at sign. Equal to 10,000. As per the reference answer. But the value of the Poisson matrix range of K. And sense of its system. Answer. Okay, nice. Very good. Let's copy this link for positional encoding. Okay. Tail in this link. Okay, let's go. Next step.
During inference or training. So we only compute the positional encoding once. When we create the model, we save them, and then we reuse them. We don't need to compute it every time we feed a sentence to the model. So why the authors chose the cosine and the sine functions to represent positional encodings? Because let's watch the plot of these two functions. You can see the plot is by position, so the position of the word inside of the sentence, and this depth is the dimension along the vector, so the 2i that you saw before in the previous expressions. And if we plot them, we can see, as humans, a pattern here, and we hope that the model can also see this pattern. Okay, the next layer of the encoder is the multi-head attention. We will not go inside of the multi-head attention first. We will first visualize the single-head attention, so the self-attention with a single head. And let's do it. So what is self-attention? Self-attention is a mechanism that existed before they introduced the transformer. The authors of the transformer just changed it into a multi-head attention. So how did the self-attention work? The self-attention allows the model to relate words to each other. Okay, so we had the input embeddings that capture the meaning of the word. Then we had the positional encoding that give the information about the position of the word inside of the sentence. Now we want this self-attention to relate words to each other. Now imagine we have an input sequence of 6 words with a D model of size 512, which can be represented as a matrix. that we will call Q, K, and V. So our Q, K, and V is a same matrix, are the same matrix representing the input. So the input of 6 words with the dimension of 512. So each word is represented by a vector of size 512. We basically apply this formula we saw here from the paper to calculate the attention, the self-attention in this case. Why self-attention? Because it's the each word in the sentence related to other words in the same sentence. So it's self-attention. So we start with our Q matrix, which is the input sentence. So let's visualize it, for example. So we have 6 rows, and on this on the columns we have 512 columns. Now they are really difficult to draw, but let's say we have 512 columns, and here we have 6. Okay. Now what we do, according to this formula, we multiply it by the same sentence but transposed. So the transposed of the K, which is again the same input sequence, we divide it by the square root of 512, and then we apply the softmax. The output of this, as we saw before in the initial matrix notations, we saw that when we multiply 6 by 512 with another matrix that is 512 by 6, we obtain a new matrix that is 6 by 6. And each value in this matrix represents the dot product of the first row with the first column. This represents the dot product of the first row with the second column, etc. The values here are actually randomly generated, so don't concentrate on the values. What you should notice is that the softmax makes all these values in such a way that they sum up to 1. So this row, for example, here sums up to 1. This other row also sums up to 1, etc., etc. And this value we see here, it's the dot product of the first word with the embedding of the word itself. This value here is the dot product of the embedding of the word your with the embedding of the word can. And this value here is the dot product of the embedding of the word your with the embedding of the word is. The next thing, and this value represents somehow a score, that how intense is the relationship between one word and another. Let's go ahead with the formula. So for now, we just multiplied Q by K divided by the square root of dk, applied the softmax, but we didn't multiply by V. So let's go forward. We multiply this matrix by V, and we obtain a new matrix which is 6 by 512. So if we multiply a matrix that is 6 by 6 with another that is 6 by 512, we get a new matrix that is 6 by 512. And one thing you should notice is that the dimension of this matrix is exactly the dimension of the initial matrix from which we started. This, what does it mean? That we obtain a new matrix that is 6 rows, so let's say 6 rows, with 512 columns, in which these are our words, so we have 6 words, and each word has an embedding of dimension 512. So now this embedding here represents not only the meaning of the word, which was given by the input embedding, not only the position of the word, which was added by the positional encoding, but now somehow this special embedding, so these values represent a special embedding that also captures the relationship of this particular word with all the other words. And this particular embedding of this
This one. We'll come here. Okay. numbers 1 is okay, but why is exponential taken? That's the dance electro. Mm. Okay, we'll come back to software function. Software function later on.
And another. Let's go ahead with the formula. So for now, we just multiplied q by k divided by the square root of dk, applied the softmax, but we didn't multiply by v. So let's go forward. We multiply this matrix by v, and we obtain a new matrix which is 6 by 512. We get a new matrix that is 6 by 512. And one thing you should notice is that the dimension of this matrix is exactly the dimension of the initial matrix from which we started. 6 rows, so let's say 6 rows. These are our words, so we have 6 words, and each word has an embedding of dimension 512. So now this embedding here represents not only the meaning of the word, which was given by the input embedding, not only the position of the word, which was added by the positional encoding, but now somehow this special embedding, so these values represent a special embedding that also captures the relationship of this particular word with all the other words. And this particular embedding of this word here also captures not only its meaning, not only its position inside of the sentence, but also the relationship of this word with all the other words. I want to remind you that this is not the multi-head attention. We are just watching the self-attention, so one head.
Yep, you guessed it. Another talking head ad where somebody's talking about people making hundreds or even thousands per month.
Self-attention has some properties that are very desirable. First of all, it's permutation invariant. What does it mean to be permutation invariant? It means that if we have a matrix, let's say first we had a matrix of 6 words. In this case, let's say just 4 words. So A, B, C, and D. And suppose by applying the formula before, this produces this particular matrix in which there is new special embedding for the word A, a new special embedding for the word B, a new special embedding for the word C and D. So let's call it A prime, B prime, C prime, D prime. If we change the position of these 2 rows, the values will not change, the position of the output will change accordingly. So the values of B prime will not change, it will just change in the position. And also the C will also change position, but the values in each vector will not change. And this is a desirable properties. Self-attention, as of now, requires no parameters. I mean, I didn't introduce any parameter that is learned by the model. I just took the initial sentence of, in this case, 6 words. We multiplied it by itself. We divide it by a fixed quantity, which is the square root of 512. And then we apply the softmax, which is not introducing any parameter. So for now, the self-attention didn't require any parameter except for the embedding of the words. This will change later when we introduce the multi-head attention. Also, we expect, because each value in the self-attention, in the softmax matrix, is a dot product of the word embedding with itself and the other words, we expect the values along the diagonal to be the maximum, because it's the dot product of each word with itself. And there is another property of this matrix, that is, before we apply the softmax, if we replace the value in this matrix, suppose we don't want the word your and cat to interact with each other, or we don't want the word, let's say, is and the lovely to interact with each other, what we can do is, before we apply the softmax, we can replace this value with minus infinity, and also this value with minus infinity. And when we apply the softmax will replace minus infinity with 0. Because as you remember, the softmax is e to the power of x. If x is going to minus infinity, e to the power of minus infinity will become very, very close to 0. So basically 0. This is a desirable property that we will use in the decoder of the transformer. Now, let's have a look at what is the multi-head attention. So what we just saw was the self-attention, and we want to convert it into a multi-head attention. You may have seen these expressions from the paper, but don't worry, I will explain them one by one. So let's go. Imagine we have a...
So let's pause it here. Copy. Current time. Continue. Here. One missing piece in this equation overall step is the V. What is V? Q. KT is nothing but QT. And then he's multiplying by V. What is V is something we don't have. So we'll complete that and close it today. So this page is explaining on how step 1, creating query Q, key K, and value V vectors. Okay. Input to self-attention mechanism and the embedding vectors. Input token. Okay. And 3 special vectors: query, key, value. Okay. Derived from the embedding. So a clever process. Okay. What is a clever process? We begin with embedding vector, and during the training process, the input data is passed through. The first layer of nodes only. Wait up. Every word in the input sequence has an associated QT, KT, and matrix. I didn't get any of this piece, man. So let's say what is let's go. We start with an input vector. Integrate vector representation of all this. That's yeah. That's
One technique that we've been seeing so far is the word embedding using techniques like word to vec and glow. But here in self attention, we are going to find a vector.
VJ is equivalent. So these two are conflicting. this, she says, oh, maybe that is like multi-headed attention and self-attention is different kind of stuff. She's mixing it up. I don't know. This paper is different from what this guy has explained. But one answer that we got is V is nothing but the embedding vector as is. But is it embedding vector or embedding vector along with the positional encoding? That's not clear. One, I know it's a little frustrating, but people could actually spend more time. It's okay if it takes more than an hour. I feel I should switch from this video uh, to what the other guy's video is. So let's try this video tomorrow then. Okay, that's all guys. See you tomorrow.